The first seminar of this new academic season was the first one in the series this academic year. So we have the pleasure today to have a talk by Professor Artem Korolenko, who is an associate professor in the Department of Mechanical and Manufacturing Engineering at the University of Calgary in Canada. And he also leads the Computational Fluids and Structural Mechanics group. He is a young researcher with a lot of strengths, as you will probably see. And he's a brave guy. He has dared to co-organize the World Conference that will in computational mechanics that will take place next year. So, again, thank you for being here, and the floor is yours.
Thank you, Ramon, and thank you everyone for being here and letting me to present. I mean, that's actually the biggest seminar I've been giving so far, because I was last year on sabbatical. I visited lots of my friends and colleagues in Europe, and it's pretty good crowd. You know, I really appreciate all your time. You know, first day of September. So, should I plan for like 40-45 minutes and then Q&A afterwards? Okay, excellent. So yeah, the title of my talk today is pretty much an overview of the last 10 years in developing stabilized and variational multiscale methods. Particularly the focus in this talk would be on marine engineering and wind energy and environmental flows. So again, I would imagine many of you are familiar with VMS, and you will find lots of familiar stuff, but I hope I will show something new as well. Yeah, perfect. Video works. Excellent. Now, just a few slides on what I'm not going to be talking about today. So our group pretty much works in the three main areas. So one big one is the aerospace applications, all the way from the subsonic to the hypersonic flow in thermochemical non-equilibrium. So we are developing the stabilized methods for this type of applications, you know, 2 temperature, 3 temperature models, as well as the fluid thermal structure interaction for the hypersonic flow with the finite elements for the fluids. I'm not going to be talking about that, but if you're interested, check our website. Now, I'm not going to be talking about the fluid structure interaction. So the focus mainly would be on the fluid mechanics part. Now, our group, I would say maybe in the last 10 years or so, have developed lots of interesting applications. Okay, hope it's not going to be like that throughout the presentation. Yeah, we'll see. So this is the FSI applications for the wind energy. As you see, the references to the papers we've done a long time ago. So that's why I would really prefer to focus on something rather new. Okay, and so that kind of the snapshots of what I will be talking about today. Okay, so I will show you a unified framework that we are using for the multiphase, multi-fluid flow for the marine engineering application. The focus would be mainly on the hydrokinetic, so on the renewable energy. And then I will show you another leg of that, the application of the framework to the environmental flow with stratification. So again, the flow over the complex terrain, the stratified flows, as well as the multi-fidelity modeling for wind energy application. But as I said, the focus would be primarily on the fluid mechanics part. Okay, good. So definitely want to acknowledge, you know, the heavy lifter behind this. So it's all about my students, you know, who did that. So Ahmed Bayram, then Hao Yang Chen, and Michael Ravensbergen, and also Musadik Thalwala. So 4 of those people pretty much, you know, made this presentation possible. And of course, everybody in the group was partially contributing to the development of the framework, as well as my colleagues at you know, different places like Brown, Iowa State University, Delft, and in the near future, hopefully UPC as well. Okay, so now a little bit of motivation. So again, I don't need to explain to this crowd why we want to do a computation. Okay, so we don't want to replace experiments. We want to come up with a framework where we can complement the experiments, right? So that's pretty much the selling point. Now, you could not put the sensor all over the, you know, your structure of interest, right? So you really want to develop the, I would not say a high fidelity tool, because, you know, there may not be the most efficient, but the multi-fidelity tool okay, which allow you to obtain the information which is not readily available in the experiments. Moreover, for many applications, as highlighted here, so for example, this horizontal axis marine renewable or the floating turbine, it's very hard to even conduct the experiment, right? Because you don't want to build a system that costs you a few million just to break it, to realize that was the problem. Okay, so now it's not that easy to analyze this kind of problem from the numerical point of view. Okay, the presence of non-linearities, highly turbulent flow in the complex domain, complicated environmental conditions, large structural site, okay, and then of course the geometrical and material non-linearity. Everything should be accounted for in the framework that we want to develop. So hopefully the framework that I will show today will address those issues and how can we address them. So there would be lots of equations, in this talk, but you're all familiar with the equations, so you're not afraid of that. So what I will do, I will be jumping from wind to marine simultaneously because they actually are quite similar. Okay, just a few things will be changed there, and I will point that out. So that's why I call it a unified framework. So we're using a single Fortran code. Okay, Fortran F90, nothing can beat that. With MPI libraries, and we can easily, turn it on, turn it off to make it applicable to one or another. So we're starting with the governing equation, which is the set of the incompressible Navier-Stokes equation. Okay, for the wind energy applications, we are considering Navier-Stokes with a Boussinesq approximation. So that's your variation in the temperature, if you're dealing with the atmosphere, or variation with the density, if you are dealing with the ocean. Okay, then you have your continuity equation, and then you have an additional advection diffusion equation to govern your distribution of the temperature or the density. Okay, for the spatial discretization, so again, I'm coming from the finite element community, so we are dealing with the finite elements for fluids, okay, and as well as the higher order non-uniform rational B-splines. So kind of taking the inspiration from the IGA analysis, because I'm kind of like a grad student of Tom Hughes, so I should work on IGA and FEM, but again, not just I should, but I really have a hope, and I believe that this is the powerful tools. Okay, now for the marine engineering applications, we have the momentum equation. I apologize. I would imagine these people would not be able to see what I show, so I don't know. Probably I can switch over here. That would be way better. Okay. Yeah. At least you can see and ask questions. Hey. Good. Okay. The continuity equation is no longer the divergence free. Okay. So that's your because you have variation of the density, etc. You have an additional transferred equation to model the vapor volume fraction. Okay. The source term on the right hand side, that's specific to the cavitation model we will be using. So now I will just keep it as the general source term. Then you have an additional advection equation for the level set, okay, to model your free surfaces like the waves, etc. And then, of course, you have an additional Eikenol equation for your redistancing. Okay, so that possess the coupled multiphase, multi-fluid problems. We can deal with the cavitation and free surface simultaneously with no issue. Okay, and again, that's pretty much what I just explained, right? So your properties in terms of density and viscosity can be expressed in the following form, where the H is your Heaviside function across the interface that pretty much tell you where you are, okay, air, liquid, or vapor. Okay, now in terms of the cavitation model, so the approach we are taking is, we're not inventing the wheel, okay, so we're using the classical homogeneous mixture model, which has its pros and cons. So the pros, it is a simple model to implement. So pretty much you just have a source term. And so we are using either called the Merkle model, where your source term is linearly proportional to your pressure, or we're using the Zwaret model, which is nothing but the simplification of the Rayleigh-Placet equation. Okay, so easy to implement. Now, the cons, it relies on these empirical factors, and that's what I don't like, okay? So I will show you it works perfectly, but if you know those empirical constants, and if you know a priori what is your cavitation number should be. If you don't know that, that's pretty much where the formulation failed. And that's why I really like, and we are currently working on the phase field for the cavitation. So pretty much solving like a Cocking-Hillard equation, where you don't have to deal with those problems. So there was also a recent work from Hector Thomas, who showed the application of the phase field for the cavitation. Okay, now so the next step is you take your strong form and you derive the weak formulation out of that. Okay, using your favorite method of weighted residual, and you get the following expression, right? So that's your Galerkin form. Okay, that's your momentum equation. Then this is your continuity equation. So I'm showing this for the marine application. We slightly rearranged the term, as you probably will notice, just to make it more applicable for the computer's implementation. But again, that's nothing but your continuity equation, then your additional transport equation, then the right-hand side, which is the body force and the traction. And then it is coupled with the advective level set equation and the redistancing equation, which we modified to make it like the advective form, again, more suitable for the computer's implementation. Okay, now for the wind, what will change? Again, you don't have any redistancing, obviously. You don't have any level set, obviously. Your transport equation becomes nothing but the advection diffusion equation. Okay, and your continuity equation simply reduced to the divergence free velocity field, and you have an additional Boussinesq term that you need to deal with. Okay, so you can see just a few terms, turn it on, turn it off. So indeed, we are using exactly the same formulation, exactly the same set of stabilization constant, etc., which I will talk in a minute. Okay, now, as you know, Galerkin form is not enough. Okay, it is unstable in the presence of the advection, and you have to deal with the turbulence somehow. So this is where the variational multiscale formulation comes into play. Now, this is kind of like a general slide, so I probably can skip it very quickly because many of you are familiar with the VMS, but this is, again, just to put it in the context of the classical turbulence modeling. You can have rents where you pretty much resolve, up to the large scale in the flow. You can have LES where your cutout lies somewhere in the inertia subrange, or you can have a DNS where you resolve everything. Okay, so the VMS, it is an LES-like approach, which means our grid resolution is such that we are in the inertia subrange. Okay, so your starting point, your scale decomposition, okay, of the spaces into the core scale, resolved with the grid and unresolved, which will also imply the decomposition of the solution and test functions. Okay, pretty standard. What do you do next? You then substitute this decomposition into your Galerkin form, and you project it into the fine scale and the coarse scale. Okay, so now can you solve? So what do you now need? Okay, you pretty much need to know what is your U prime to close the system. And how do you do that? You solve your fine scale. Can you solve it exactly? Of course not. Okay, if you can, you go and you claim your 1 million prize for solving the Navier-Stokes equation. Okay, so the strategy is to obtain an approximate analytical expression, okay, for your small scale quantities. The next slide, for probably many of you, actually, how many of you are familiar with the VMS concept? Okay, so probably I should slow down then because I'm kind of going quickly on that. So now let's take a look a little closer at the fine scale equation, okay? Because as I said, we want to come up with this approximate solution. I will write it using the projector operator, okay? So it's your momentum equation, continuity, and the advection diffusion, okay? So now it will be all about what kind of projector operator you select. So it's very similar in terms of notation, and I made it on purpose to a recent paper of Ramon and colleagues, right? And here you can see on the right-hand side, we have this function, which pretty much guaranteed that your right-hand side is still infinite dimensional, okay? And so then what you do is you pretty much start thinking about the approximation. So what you can show that your equations can be approximated in the following way, okay? And now you have a variety of choices about these functions and how do you project the residual. So what we do, and for our application, it works very well, we take the simplest way, okay? So we are considering the algebraic quasi-static subgrid scale model, okay? Which means these functions, they are zero, and your projection is nothing but the identity, okay? So we are taking our small scale to be simply proportional to the residual of the large scale, where the proportionality factor is tau, okay, which originates from the stabilized method for the fluid mechanics. As I said, this approach for all of the application presented works very well, but I know there was a work which was shown that, you have to go with the dynamic subgrid, or you have to consider the orthogonal subgrid scales. And we start hitting that problem when we start dealing with the reduced order model. But for the full order model presented here, this simple approach works quite well. I mean, I call it simple, but I mean, it's not really simple, okay? So for the tau, we're using the standard diagonal definition, okay? Where, again, I'm not gonna go in too much of the details about that, but again, the way you design the stabilization parameter is you want to pretty much stabilize the flow in the presence of your inertia, advection, or diffusion, right? So that's how you come up with the structure of those terms. Okay, now for the marine applications, it's exactly the same approach, but you just have a few more variables that you have to deal with, which is your level set and redistancing and distance function. And again, same thing, quasi-static small scale with the algebraic subgrid model. So here, your residuals is your nothing but your momentum, continuity, transport equation, level set, and then redistance. Okay, which again we define this advective velocity to kind of simplify the notation. Now, for marine applications, however, is UPG itself, or stabilization itself, is not enough. Okay, because of the sharp gradients associated with your free surfaces or cavitation or whatever. So we actually put an additional discontinuity capturing operation. Okay, we're using the pretty standard gradient-based discontinuity capturing, which is also proportional to the residual. Okay, now you can see that everything is proportional to the residuals at the end of the day. Why? Because you have the method which is consistent. Okay, as your residuals goes to zero, all of these additional terms goes to zero. So you're not introducing any additional dissipation into the system. So for the discontinuity capturing, you equip the following terms with that. So your volumetric vapor fraction, then your level set, and then your resistance. Okay, so that pretty much will stabilize the formulation in the presence of the sharp gradients. Okay, so now you thought that was complicated. Now you take all the pieces together and you show the complete coupled formulations. Okay, so let me grab some water. I realize I will probably skip some parts later on just to make sure I stick with time. But now, so we can define our governing equation in this nice simple bilinear form. And so let me show you what this bilinear form looks like when we put all of the components together. So first of all, you have your standard Galerni, okay, which we said is not enough, it's unstable, that's all. Now you start getting an additional term that looks like nothing but interaction between the large scale and small scale, like u prime, u, and then interaction between the small scale and small scale, u prime. So if you are familiar with the classical turbulence modeling, that's your classical turbulence modeling representing your, across stress and Reynolds stress. So that's why we say that VMS is a turbulence model. When I say that for the classical fluid mechanician, I got hammered, but it is, okay? So how does that term looks like, okay? So you have pretty much an interaction between the, so this is your cross stress term, another cross stress term, then Reynolds stress term, which is u prime. Now you have an additional term for the small scale pressure, okay? So that's your least square on the incompressibility constraint. And you have this term, which is originating from the PSPG, okay? So that pretty much allows you to use the equal order interpolation for the velocity and pressure, satisfying as such the Babushka-Brezzi condition, okay? Then, so okay, that's your continuity and momentum. Then you have an additional term, which is nothing but SUPG only, okay, for the transfer equation. Then you have your discontinuity capturing, and then you have your right-hand side. Okay, how does it change for the wind? It just gets simpler. Okay, so definitely no discontinuity capturing. Okay, your continuity equation reduces to the divergence-free velocity field with a Boussinesque term. Okay, your transport equation becomes your advection diffusion equation. And you have now additional term that corresponds to the interaction between the small scale velocity and the small scale temperature. And that's very important. I mean, you can actually investigate the importance of that term, but in our application, we found to keep that term is important. And then you also have additional term for the small scale Boussinesq and the right-hand side for the heat flux. Okay, good. So now for the marine, the level set formulation is pretty standard. It's nothing but the SUPG formulation. Okay, so your classical Galerkin plus SUPG plus discontinuity capture. Okay, same thing for the redistancing. You have your Galerkin form, you have your SUPG, and then you have your discontinuity capture. Now, based on our experience, we also find out that when you do reinitialization of your level set function, your levels, your function can go unstable. Okay, it can be mainly due to the discretization error. So we come up with this additional penalty term to pretty much stabilize these deviation across the interface. So you can see it pretty much acts only across that interface and do not affect the flow away from there. Okay, and then the right hand side. Now a few more components before I jump into the application side. So if you're dealing with the fluid mechanics and the wall-bounded turbulent flow, you know that pretty much the beast that you have to deal with is your flow near the wall. Okay, so how do you treat the Dirichlet boundary conditions at the wall? Okay, now we want to have an efficient numerical tool, which means we could not really afford a y plus less than 1, to fully resolve the turbulent. So what we did, we pretty much impose the Dirichlet boundary conditions weakly. Okay, what does it mean? So, following the Nietzsche's approach, we can add an additional term into the formulation, which looks like this is your consistency, a joint consistency, and the penalty term. Okay, so by adding that, it's like also you can draw a similarity with the DG-like approach. Okay, and so you are allowing flow to slip on the coarse mesh resolution, but then of course as you refine the mesh, you exactly recovering the no slip, and so that flexibility really helps. And then you can also do that for the temperature, okay, in the similar way using the Nietzsche's-like approach. Okay, now a little bit more about the weak BC. So you can do this original definition where your penalty term defined in the following way. Okay, the constant, which is defined based on the inverse estimate, so you have the optimal range of the values, and it's proportional to the properties and the mesh size. So in most applications that works well. However, in some applications you are required to incorporate the actual wall model into your weak BC. And again, this was shown by Professor Hughes and his colleague back in the days. And we do have that as well. So we can also use the actual wall model weak BC. And we also recently extended that one to do a wall modeling for the temperature, as well as we incorporated the wall roughness into the weak BC formulation. And I show you the cases where having that wall roughness and the wall model weak BC is critical. Otherwise, you pretty much would not get anything in your solution. Now, okay, I will probably skip this part. So again, a few more slides, because again, we're dealing with the flow, the objects in the relative motion. So we're pretty much using the sliding interface between the stationary and moving domain, and we're using the same Nietzsche's idea, but just lots of equations. So if you don't mind, I will fly through. We can always come back to that if you want to. But they look complicated, but it is the same consistency, a joint consistency and penalty term. But now you are not dealing with the fluid and wall, you're dealing with the fluid and fluid. That's pretty much where it is. Okay. Good. So now the numerical algorithm. So we are for the time integration, we are using the generalized alpha method. Okay, which now we start exploring. It has its pros and cons, but for the full order model presented here, it works perfectly well. It's second order accurate, implicit, unconditional, stable. The Newton-Raphson method is used as the nonlinear solver. So we derive all of the Euler-Jacobian matrices by hand, a good exercise for your students. They're very happy about that. And then for the linear solver, we are using the GMRAS with most of the time, a simple diagonal preconditioner works well. Now we also can do the full, inverse of the matrix, like LU preconditioner, etc. But for all of the cases presented here, the block diagonal preconditioner gives a very good, solution. Yeah, that's how does it look like in the matrix form. So you have so this is like for the marine, you have a block of the coupled momentum continuity with the transport equation. So you solve that, you update your solution, then you solve your level set, update the solution, you solve your resistance set. Okay, well, this is just what the residuals looks like. For the marine, for the wind, it's just nothing but the coupled Navier-Stokes and the advection diffusion equation. So pretty easy in that case. Good. Now, one more component, which is very specific to the wind energy application, because as I said in the past, we've been working on the high fidelity FSI study, where we've been fully resolving the blade surface. It is a great approach, very accurate for the single turbine. Now, if you go to the wind farm, which has 50 turbines, that's just computationally unfeasible. You could not really deal with that. So what we did, we developed the multi-fidelity approach. So instead of doing the fully resolved blade, we adopted something called the Actuator line model. Okay, so it's a very well-known approach in the wind energy community. What you do with that is pretty much, so let me show you this cartoon. So you take your blades, okay, and you subdivide it into the number of actuator points, okay? In that point, you have the information about your profile, like geometry, etc. Then what you do, you sample the velocity at that point, okay, from the surrounding. Then you use that sample velocity to compute the aerodynamic force F using the classical blade element momentum theory. And then you project it back on the background mesh as the body force, okay, which will go directly into your momentum equation in the Navier-Stokes, okay? So this is it's called the Gaussian projection loop. And so you repeat pretty much for every point as the blade rotates, and you kind of mimic the presence of the blade on the surrounding fluid, okay? So now, finally, let me jump into the application. So that's, a unified framework that we have. So let me start with a few cases in marine hydrokinetic turbines, okay? So the first test case, let me show you how well we can deal with the free surface, cavitation, and then the coupled free surface plus cavitation. So this was the experimental test case that was done at the University of Southampton. Again, it's the horizontal axis turbine. You can see all of the parameters. We're just dealing with the classical linear tetrahedra finite elements, okay, nothing more than that. You can see in this case, the whole domain is rotating because, again, sliding interface is a nice feature, but it adds the computational cost. So if we can avoid it, we will avoid it. If we could not avoid it, we deal with the sliding interface. So here's the results for the cavitation case. Okay, now, first of all, we want to make sure that for the non-cavitating case, we get a good agreement. So we did the comparison with the wetted flow regime. Wetted means non-cavitating. So in the water tunnel, you can have the same rotational speed, the same incoming velocity, but just changing the reference pressure will tell you whether you trigger cavitation or you don't trigger cavitation, okay? So you can see for the wetted flow, we are matching quite well on the pressure and the thrust coefficients. Now, for the cavitation, unfortunately, they didn't provide the quantitative value, for the CP and CT, but they provided the qualitative picture showing the formation of the cavity on the surface. So the cavitation is forming on like a 15% of the tip of the blade. Now, interesting thing, if you will see on the value, because of the cavitation, your CP drops by almost 30%. So if you do not account for that during your design and you have a cavitation, boom, 30% loss of the power, premature failure, etc. Okay, I'm not even talking about the collapse of the bubbles, etc., etc., just from the pure hydrodynamic performance. Now, the interesting feature here, if you look at the vortices, right, as the cavitation start forming, you start developing this like a horseshoe vortex structure originating from that cavitation. Now, the next step, they also did experiments in the free surface tunnel, okay? So the same turbine, similar conditions, but in this case, because like a square domain, we have to deal with a sliding interface. So we put cavitation, level set, redistancing, everything across the sliding interface. So that's something that hasn't been done in the open literature up to now. Like recently, the paper was accepted in CMME for this test case. So here, they do have the quantitative data. Okay, so again, the wetted flow conditions on the top, and on the bottom is the CP and CT when you have a free surface. Okay, you can see again a very good agreement between our framework and the experimental data. Now the drop is not as significant as when you have cavitation. So you see about maybe, you know, what is it, like a 6% or 8% drop in the CP. Okay. So now we said, okay, cool, we validated cavitation, we validated free surface. Now let's do a proof of concept of the combined free surface plus cavitation. Of course, it's almost impossible to do that experimentally, okay? So we said, yeah, let's explore how does it look like numerically. So, of course, there is nothing we can compare to, but we run a coupled cavitation plus free surface. Now, we are not yet interacting with the blade is not passing through the free surface. So that's the next step we really want to explore, right? So this like a super cavitating, you know, a flying hydrofoil stuff. So that's the work in progress. But you would see that when you combine these both effects, you drop in a performance is almost 38%. So significant. You know, if you underestimate that, like your machine will completely, you know, output, like, you know, underperform. Good. Now, for the sake of time, I don't have, you know, opportunity to talk about some other cases we did on the marine renewable. This is the work we done with the New Energy Corporation, looking at the vertical axis hydrokinetic turbines. It's another beast because your flow pretty much changing from fully attached to fully separate within one revolution. And so you have this complicated down wake effect where the wake from the first blade propagates and the second blade hits that. So your formulation better to be robust and accurate to capture that. And we did quite accurately. We also implemented a various synthetic turbulence generation techniques like STG, RFG, SEM to investigate the effect of the incoming turbulence on the turbine performance. Again, let's see how much time we have. Okay, I can probably, I mean, that's the work we, again, done on the vertical axis turbine. We come up with a more efficient design. So that what was a company had originally. So it's called like a quarter strat location. And so what we come up with, we say that you can actually put your struts on the top, okay, at the tip of the blade. And we investigated that one in the presence of the free surface and the different immersion depth, okay? So we pretty much showed that when you modify your strut location, you can gain almost 15% of power production. But it was from the pure hydrodynamic point of view, because what is bad about that design, from the structural point of view, you have pretty much a doubly supported beam, which will start developing, you know, pretty much lots of oscillation. So we are now doing the pure structural analysis and FSI on that to really investigate the problem from the structural point of view. Also, you can see as soon as you put your struts at the tip, you have this huge deficiency in the wake, you know, and normally you arrange these systems in array. And so that also should be taken into account. And then that's just the a point of view from the free surface, because these units, they're installed on the barge. So you also make sure that there is not much free surface movement such that it becomes more stable, okay? Good, okay, let's see, I have 7 minutes. So let's talk about some wind energy applications and environmental flow. I know I'm going a little fast. I don't know if it's a good and bad to cover kind of overview, or you better focus on one thing. We'll see, okay? But if you have any questions, I can go back and spend more time discussing in details about that. So now let's start with the classical channel flow. What can be better than the channel flow? Okay, so but in this case it is a stratified channel flow, okay, and we want to show how our results compare with the DNS, okay, on the way coarser meshes. So what we're doing here, we're looking at the different stratification regime defined by the Richardson number, like 18 and 120, and we're using the quadratic NURBS and weakly enforced boundary conditions here, okay? And keep an eye on the grid resolution between the VMS and the DMS, okay? Now, an interesting feature about this flow is that it has a strong intermittency. What is the intermittency? Is that you have a turbulent flow, and then you have a laminar patches inside of that flow. So now if you're using the classical turbulence modeling, what do you use? Are you using the turbulence model, laminar flow, or transition, or specifically designed intermittency model? In our case, no tuning, no switching of the parameter. So literally all the cases I'm showing today, exactly the same set of constant, independently of whether it's finite elements or NURBS. So no tuning involved. I mean, you probably can do a better job if you start looking at those parameters and kind of adjust them based on the element size. But we found that, you know, the formulation we have is pretty unified. Okay, so here the top is the VMS qualitative comparison, and on the bottom this is the DMS results. Okay, so you can see qualitatively it's agreed quite well in terms of capturing this intermittency. Here is the quantitative comparison, and so let me tell you what is what. So the triangles, it is a Richardson of 18, so it's pretty much like when you almost have no stratification. And then the crosses, this is the Richardson number of 120, okay? And this is the DMS. So the reason we put the triangles, I also want to show what happens to the flow when you have a stratification. So you can see your turbulent quantities changes quite a bit, okay? And here we're looking pretty much at the blue and red line, okay? We will also explore a different definition of the tau, because when you deal with the stratification, what you have in your momentum equation, that Boussinesq term pretty much triggers a coupling between the vertical component of your momentum equation and the advection diffusion equation. So ideally, your tau parameter should be modified such that instead of the diagonal term, you also have a term that corresponds to that coupling. I mean, in our experience, we did this test and we found that, I mean, it improves a little bit, but it's, you know, pretty much the diagonal form of your tau works quite well. We also look at the different flow regime with the different friction Reynolds number. And the results you can see agree quite well with the DNS data. Now, this is an interesting case. So we did the comparison with this field test experiment. It's called BASE, okay? So here, the problem is to capture the formation of these low-level jets, okay, over the top of your boundary layer, okay? In this case, we're using the wall model based with WIG-BC with the wall roughness. If you don't do that, what you get is pretty much a gradient, okay? You don't have this low-level jet formation, which will trigger that, you know, this behavior. And again, qualitatively and quantitatively, the results agreed quite well with the experimental data as well as the numerical data from other researchers highlighted in the gray shaded area. Okay, now a little bit more interesting test case, because we're also interested in dealing with the flow over the complex terrain, you know, like hills or islands or, you know, you name it. So there are few well-documented test cases. So one is called the ballooned hill. So this was the field test campaign designed to validate the numerical tools. The good thing, I mean, good thing for us, bad thing for the numerical people in general to deal with this, it has a very sharp, you know, point here, and then it also has the circulation, which is recirculation, which is happening on the lee side. So that's kind of the two most critical zones. The good thing, it has all of the masked data, which we can compare to. So here is the comparison with the experiments, as well as, you know, LES and RANS tool. So here, the turbulence is generated using the precursor simulation, which we did use in the past. I don't like that approach because it adds up in an extra computational cost. So if I can, I really prefer to go with the synthetic method, okay, like SEM or RFG to generate the turbulence, okay? So here, let's take a look at the few locations. So right at this sharp, you know, interface, and we are here in blue. So we pretty much agree exceptionally well, you know, as well as on the lee side, we are pretty much right within the uncertainty. Now, the thing that I kind of want to understand better is why on the very simple part, where it's like a flat terrain, we are pretty off. Okay, so I don't want to question the experiments, but that could be also one of the reasons, because how come we can be very good at pretty much all difficult locations, and on the very flat surface, we are, I mean, it's not completely off, but we kind of a little bit away of the uncertainty. But overall, the framework performs very well. And this was the test case where we compare the quadratic NURBS with linear finite elements. I know it's not a valid comparison, but we showed that even coarse quadratic NURBS will outperform fine linear finite elements on these type of problems. Okay, and here we used the single patch for the NURBS. Okay, so there's no discontinuity like C0. This is just a different point of view on the velocity as well as the turbulence statistics. So you can see the comparison between the finite elements and medium NURBS. Okay, so overall good agreement. And we also look at the a more complicated test case. So it's the field test experiment from Portugal. It's the Pertijão terrain. So it was a part of the European Wind Energy Atlas. So it's like a what is it, like a 6 kilometers by 3 kilometers by 3 kilometers terrain. And so we actually attempted to model that with both linear finite elements and quadratic NURBS. So here's the results of FEM. Now, we didn't use any mass data. So our boundary conditions is just a doubly periodic. Okay. And I was very surprised when, with such a simple boundary condition, we can represent the actual measurements quite well. So what we're doing now to make the formulation more, to allow the more realistic flow field, we're coupling our VMS with the VRF model. So it's like a weather prediction. So to account for this mesoscale effect. Okay. Good. One more case in this complex terrain. So I showed a pure stratified flow. I showed the flow over the complex terrain. Let's combine them together. So this was a stratified flow over the complex terrain. Some people would think the Gaussian hill is not complicated. Good luck to model that. Okay, so the problem here is based on the level of stratification defined by the Froude number, your velocity is changing the trajectory. Okay, it's either go on top of the hill or it's either go to the side of the hill, and you start developing this recirculation, this hydraulic jump behind the hill. You can also think about it as the island. Okay, and you try to model that with your weather prediction model. Completely impossible. They're pretty much acknowledged that they could not capture that phenomenon. Again, this is just some comparison with the experiment in terms of qualitative and the different point of view on that. Now, a very last test case, because again, I introduced this actuator line model, so I want to show how does it perform. So we did the validation on the several wind turbine benchmark cases. So we started with the very well documented NREL 5 megawatt wind turbine. So linear finite elements, okay, this is your Eulerian grid, so the grid doesn't move and your ALM simply rotates within that fixed domain. So we look at the grid convergence study, at the refinement on the wake, the refinement at the rotor to show that the method is indeed converging. Okay, you can just qualitative comparison as well as the quantitative comparison. We also look at the turbine in the presence of the stratification. So we took our 5 megawatt NREL and we feed in the stable atmospheric boundary layer that we generated with our colleague from UC San Diego. And immediately you see that in the presence of stable stratification, you have almost 37% loss in your power production. Okay, which is significant, right? Because you design your turbine to be a standalone unit operating in the uniform flow. You put it in the farm and it breaks. Why does it break? Because there are lots of assumptions that you are making, in terms of that. And so that's where we're currently working with some industry partner in Canada to address that, optimal wind farm operation and control. Again, just a few more test cases. What happens when you put turbines next to each other? Again, you see almost 70% efficiency, right? That pretty much should tell you that, it matters how you arrange them. Okay, you could not just put them in line. You really need to, be a more sophisticated on that. Okay, and again, here all the simulations was done like, within a few days. So that's pretty much what the multi-fidelity gives, because if you want to do that with a fully resolved CFD, a few months, okay, that probably what will take you on the 2 turbine. Yeah, we also look at the 2 turbine in the presence of stratification, where the stratification actually helped, because with the stratification, you enhance the mixing behind the turbine, and as a result, there is less deficiency on the second unit, and so the power drop is only about 20%. Okay, now that's all I have, just a few slides showing some ongoing efforts. Okay, on the marine engineering side, we are looking into a few things. Again, we are working with the ship propellers. We are working with with the propellers, with the ship hydrodynamics. We're looking into the cavitation for the vertical axis hydrokinetic turbine. We're also modeling the large scale vertical axis turbine. So this is the 250 kilowatt unit, which is will be installed in the Bay of Fundy in Nova Scotia in Canada. We also try to develop a multi-fidelity approach for the vertical axis turbine, similar to what we did with ALM for the horizontal. So such that we don't have to fully resolve our blades, and we try to incorporate the complex terrain, because when you put this unit in the ocean, there is still a complex terrain that affects your velocity and affects the performance of the system. And of course, we're also looking into the fluid structure interaction. Now on the wind energy side, we're extending the formulations to deal with the whole wind farm. So this is the most recent work. It's still kind of in progress. It's like about 50 turbines. So we are modeling with ALM the whole Lillgrund wind farm, and we're looking into like an optimal wake control. We're also looking into the wind turbine in the complex terrain. So we take the same Perdigão hill, we take our ALM, and we kind of put it on the top. And so what happens, the wake that develops from the turbine, it actually follows the terrain. So your whole idea of the wake mitigation completely changes when you have a terrain. So it's no longer flat, it's no longer follow that way or that way. Terrain does matter. And then a very, very recent work, I mean, we lost this like a hype train with the reduced order modeling, so we're kind of catching up with that, and try to put everything into this POD-based ROM, as well as to explore some physics-guided machine learning techniques. Okay, some of the references, and probably a very important slide. We are looking for collaboration. Okay, we do have joint funding opportunity, mobility for students, and we have in my group a lot of open paid masters and PhD student positions. I don't want to steal anyone, but if you have smart friends who are not afraid of mathematics, and programming, well, yeah, you see, students are happy. They're also happy inside of the lab. Like, please. And yeah, as Ramon mentioned, so I'm the chair for the World Congress and the Pan American Computational Mechanics Congress in Vancouver, together with my co-chair. So I hope I will see many of you there in July in 2024. So thank you so much.
Thank you very much, Artem. Are there questions?
Feedback. Yeah.
So I get the impression that whenever you can, you avoid using turbulent models with your LES, apart from the intrinsic
VMS is the turbulence.
Yes. And have you encountered situations where you needed to switch, use some other model because it wasn't working?
No, only VMS. So exclusively SUPG. Now, what I can do in some cases, SUPG itself works very well. So, those additional cross-stress terms from the VMS might not be very important. For example, some of the work we're dealing with a compressible flow, we found that SUPG itself works exceptionally well. So we can capture the large-scale structures very good. Now, when you start dealing with the flow, like, I don't know, smooth body flow separation, there, the importance of these small scales really. But yeah, no, VMS or SUPG, so I stick to the stabilized finite element method, yeah.
when you do finite elements, you basically stick to the plain vanilla linear tetrahedron.
Yeah, linear tetrahedron. Yeah.
And when you do splines, you go as high as cubic, or have you tried higher?
No, we actually done quadratic because again, yeah. So no more than quadratic NURBS because again, now the NURBS you saw the results are good, but there is a cost. Okay, let's be honest, and the cost is the computational cost. Okay, your bandwidth increase and it becomes actually not very efficient. Now, another problem with NURBS is the generation of the fluid mesh for the complicated domain. Because as soon as you need to build a multi-patch fluid NURBS mesh, good luck. Yeah. So.
Thank you. I have many questions, but please.
I know.
No, but I'm not going to ask them. Not going to ask them all. Don't be scared. So.
I'm ready.
Maybe while the audience is thinking about another question, let me make one of them, which was surprising to me because you said that you are using exactly the same constants for linear elements and quadratic NURBS.
Yep.
That I think is quite strange because I would say that the constant in the inverse estimate in the case of quadratic NURBS is much larger than in the case of linear elements. So.
But they're the same order of magnitudes, right? It is an order.
Oh yes, the order of magnitude is the same, but the value should be at least.
Yeah, that was surprising to me. But
you're using exactly the same constants.
Exactly the same. Same thing when we go with the finite elements and we're using linear tetrahedra or hexahedra elements. So technically, you should change your constant based on the element type.
No, but that's very close. I mean, tetrahedra and hexahedra have a very close inverse constant.
Now, okay, that's actually a good question because we're using the same constant for FEM for all of the cases. For the NURBS, I need to check because for NURBS we might be using a different, but I need to check that.
I would say it should be at least a factor of 5 larger.
Okay,
that's what I would say.
Well, I can easily check the code, but.
Talk about another question. You can make another one.
Yeah.
We had a lot of trouble with boundary conditions for stratified flows. Everyone knows that. What are you using there? And the reason is very simple, because I mean you cut the domain and that boundary.
Yeah, your pressure doesn't. You need to know. So yeah, okay.
That boundary is completely artificial, and you have to do something otherwise.
So the early thing that we did, we pretty much computed the average pressure profile based on the inflow. And then we put that average pressure pretty much on the outflow. So you pretty much have an additional term that you put in your weak form to weakly impose this pressure. Okay. In that case, you're not developing. So if you don't do that, if you just have traction free, you're pretty much developing this profile. Okay. If you put this average pressure, everything works well. But after that, we actually did the more robust approach where you put again an additional term on the outflow that pretty much mitigates that problem completely.
Yes, that's what we had to do. In the case of non-stratified flows, you certainly put just, let's say, the hydrostatic pressure, so to speak. So
we do a standard traction free.
Well, this is if you don't consider gravity. But if you do consider gravity, you have to put the hydrostatic pressure, and that's it. But in the case of stratified flows, in which density changes point-wise, then we have to be very careful with that. So.
Yeah, no, we put this. I try to remember the paper from which we implement, but I can show you. It's again very simple. Like you add a few terms, which pretty much help to stabilize.
Yes, in our case, what we did was to add a penalization term which did not allow the flow to come back to the domain.
No, yeah, we have that. We have that reverse outflow. So it's very similar to that outflow stabilization term, where you pretty much calculate if your U times N is negative, right? When the flow. Yeah, so we're using very similar.
Yes.
Yeah, we're using a similar approach. But in the very early, as I said, even this simple, you compute the average pressure at the inflow, and then you put it on the back. That works. That works well. Then you have to pre-compute it, which I don't like.
Any other question? maybe I'll make my last one then. I mean, it's really not a question. It's just that I said that you are a brave guy, but I really think you're a brave guy. You said that you're using just Newton-Raphson everywhere. Is that true?
That's exactly true.
Wow.
So you pretty much with a 3 to 5 nonlinear iteration, and then about.
No, but the problem is how do you linearize all the nonlinear?
We have a. Oh, that's a very good question. So I will point you to the paper. Oh my, I had a very good PhD student. So yeah. So now, first of all, there are various choice of linearization, because everything is coupled, but some of the coupling you can ignore to pretty much improve your convergence. So we showed for the so the most complicated was this cavitating case with the free surface.
With the source. That
Exactly. Oh, that's a good question. You have to linearize the source term, which has a square root function.
No, and the inverse of something, and so
we did that. We did that by hand. Yeah, we did. We derived all of the linearization, and we showed the 9 different linearization choices. And we pretty much show which one is pretty much give you the best.
I would bet you have a mistake there.
Yeah, let's bet.
It's impossible to do that.
No, but with the square root, what do? You pretty much approximate, because the problem with the square root, you have the discontinuity, right? So when you plot that function, so when you do that, you have to pretty much kind of approximate this discontinuity over there. So we've done that, and then by hand just deriving all of the criteria was fun exercise. Because are you using the AD or what do you do for the?
No, we used in several terms we use Newton-Raphson, but in other terms we use fixed pointer scheme. So
fixed pointer, because I know people they also go right now to the automatic differentiation to pretty much say I want to forget about the
there is some difficult terms we keep them frozen and use a fixed point method there. And for the others, for example, for the collective term, we use Newton linearization, but not everywhere. We don't dare. We are not so brave as you are. Okay. Any question? So thank you very much for this talk and congratulations.
Thanks. Any comments, any feedback, any mistakes, always welcome. So very example, we're developing compressible flow. We've been developing that for 2 years. It didn't work, and then we found the typo in the code. Everything started to work. And we in a few months developed to the hypersonic non-equilibrium. So that could be some type of somewhere.